and get the presentation. Okay, so we're going to try to bludgeon our way through this Brayton cycle. This may have been more than we needed, but our purpose is to get to a combined cycle, and combined cycle is half Brayton cycle and half Rankine. So I decided to go ahead and do this. I don't know if it was a good decision or not, but anyway, this is the slide we wound up with last time, which is just, doing the energy balances, applying all of our assumptions, negligible kinetic potential energy, adiabatic components, no pressure drop, stuff like that. And so, we just get the enthalpy difference across all those components. And then we can go ahead and write the thermal efficiency. It's the turbine work per unit mass minus the required compressor work per unit mass divided by the combustor heat input per unit mass. And there's all the enthalpies that are just filled in from those definitions right there. So that's all pretty straightforward. And the back work ratio is, so before in the Rankine cycle, we had the pump work divided by the total turbine work. Here, it's just the compressor because we don't have a pump. So the compressor is the parasitic work required to run the cycle. And notice that on the Rankine cycle, that back work ratio was like 1 to 2%, could even be less than 1%, depending on the particular problem. Here, this back work ratio, because we're compressing a gas, is potentially between 20 to 80%. In a real cycle, it's probably going to be between 30 and 40%. But it's a bunch, and that's, it takes a lot of energy to compress a gas, whereas a fluid being almost incompressible, not so much. And this comment is just saying that all these enthalpy differences apply whether we have irreversibilities present or not. We develop them from going at the argument for, isentropic and irreversible and all that, but those enthalpy differences still apply even if there's irreversibilities present. So we don't have to rederive anything. Okay, so the simplest way to start is the ideal air standard Brayton cycle, which makes a lot of simplifying assumptions, but it makes it pretty easy to work problems. So I think this is probably redundant a little bit, but anyway, frictional pressure drops are absent for flows through heat exchangers. These processes occur at constant pressure, known as isobaric. Flows through the turbine and pump are adiabatic without, they're irreversible, or they're reversible without irreversibility. I think that's a double negative, isn't it? My English teacher would have gotten on me for that. But they're isentropic in this ideal air standard Brayton cycle. So the Brayton cycle breaks down to 2 isentropic processes and 2 isobaric processes. And it turns out the ideal Rankine cycle also has 2 isentropic and 2 isobaric processes. Okay, so let's look at some diagrams here. So the ideal air standard Brayton cycle, we've got our 4 internal reversible processes. So we're gonna compress the gas, isentropic compression in the compressor. And so we're gonna go from 1 to 2. So on the PV diagram, note that 1 to 2 kind of swooping upward line. That's a line of constant entropy on the PV diagram. And obviously on the TS diagram, it's a straight vertical shot up from 1 to 2. Heat transfer to the air as it flows at constant pressure through the high temperature heat exchanger or the combustor is going to take us from 2 to 3. So on the PV diagram, we're going at constant pressure, but as we go to the right, we incur higher and higher temperatures. And likewise, on the TS diagram, we see the temperature go up and the entropy increase as we go from 2 to 3 along a line of constant pressure. And then the isentropic expansion of air through the turbine is going to be from 3 to 4. So this is on the PV diagram, that's another line of constant entropy, just a larger value. And on the TS diagram, we just come vertically straight down if we're isentropic. And then we have to put in at least that maybe fictional heat exchanger to close the cycle to get us, because we're coming out of that turbine pretty hot. And so we got to get back to 1 to close the cycle. So we envisioned a heat exchanger, and it gets us from 4 to 1. And we have closed the cycle. Okay? So anybody jump in out there if you got questions, but this is pretty basic stuff here. So if you write the first law, and again, we throw away kinetic potential energy effects. So you get just the work of the control volume per unit mass. And so this is for internally reversible processes. We're going to do some substitution here in just a second, and that's equal to the heat, the rate of heat transfer per unit mass, again, internally reversible. And we've got H1 minus H2, the enthalpy difference, and we throw away kinetic potential energy. That's just the steady state version of the first law with the work term taken over to the left side of the equation. Okay. And so if for internally reversible, remember that Q dot CV over M dot is the integral from 1 to 2 of TDS, okay? And so we're just going to make that substitution in there. And now that's only for internally reversible heat transfer, but it works nicely in this case for this assumption, okay? So we got rid, it's the same equation, the first one and the second one, except we made the substitution that integral 1 to 2 TDS is equal to Q dot CV over M dot, okay? And then we're going to make the assumption, the quasi-static process, that the process from 1 to 2 is a series of equilibrium states as we go through it. So all of the property relations hold. Then we can use the TDS relation that you see at the bottom. And so we're just going to integrate that relation on the bottom from 1 to 2, and then we'll write the result up above. And so we did. So, you know, we get the integral from 1 to 2 of TDS, and the DH integrates into H2 minus H1, and the minus VDP is integral from 1 to 2 of VDP, okay? And so now we're going to substitute for this TDS, which right here, the TDS from the other equation. So I say we got TDS is equal to H2 minus H1 minus the integral 1 to 2 VDP. And notice when we put in that H2 minus H1, it's going to cancel H1 minus H2. So this is going to actually simplify for us. And we wind up with that for internal reversible processes, steady state and all that stuff, that the work per unit mass, you know, the control volume is the negative of the integral from 1 to 2 of VDP. And, you know, where's that come from? Just this little derivation is where it comes from, right here. So you can have any question, go back and look over that. It's pretty straightforward, really. And so then this really is the pump trick, right? So if this is where the pump trick this is the derivation of the pump trick, really, that we use for the Rankine cycle. We're also going to use it for a gas here. But notice, if this is basically an incompressible liquid, then the specific volume is going to be constant, and that pulls through the integral sign. And so then we get minus V times, and you just integrate the dP, and bingo, you're in good shape with this relation. And so that's what we use on the pump, and we just kind of throw away the minus sign because that's just tied up in the thermodynamic definition of positive work. But we know what direction, when you run a pump, you know that the work's going in, right? We know so anyway. And then if we're doing a gas, we'll go ahead and use this relation up here because specific volume is not constant. Okay. All right, so what's this mean when you look on a PV diagram? Well, it means if I compress, if this is, reversible, internally reversible, in a nice ideal process, if I compress from 1 to 2, this area behind the curve over here to the left represents the work per unit mass, okay? So that's the derivation we're trying to get to. And then, so we're going to use that going forward. So let's see, since this ideal Brayton cycle, we're just using internal and reversible processes, then we can use this area behind the curve relationship in our analysis. And we see that, well, the compressor work input is that shaded region, which is the negative integral of VDP from 1 to 2. And guess what? The turbine work output represents that whole big area from the pressure axis, the y-axis, all the way over to the curve. And the enclosed area represents the net work, which is going to equal the net heat. So we should be good on that. Okay, and so again, for internal reversible, we also have the areas under the TS diagram. So we can look at that. So this area, 2, 3, AB2 represents heat added in the combustor. And this smaller area, 4.1 BA4 represents heat rejected in that heat exchanger in order to close the loop. And bingo, the area enclosed represents net heat, which is the same as net work developed. So we just need to touch those bases. I kind of give a quick review to everybody. Okay, so this pressure ratio, P1 to P2 across the compressor is an important parameter when operating gas turbines. And so we're going to have a couple of slides here that kind of illustrate that. So what this would mean is we've got some initial pressure ratio where, the compressor was P1 to P2, and then this is our cycle. And we said, well, now hold on, let's up that exit pressure from P2 to P2 prime, and then our cycle, instead of stopping at 2, we'll go up to 2 prime, 3 prime, down to 4 and back to 1, and then we're going to make some observations about this. Okay, so, what can you say? The heat is added here from 2 to 3, or from 2 prime to 3 prime. So it's obvious that at the higher pressure, the average temperature during the heat addition is going to be greater. And so since we're coming down, the bottom part of the cycle is all the same, that increase in pressure helps the cycle efficiency because it increases the average temperature during the heat addition. Okay. Accordingly, Brayton cycle thermal efficiency increases with pressure ratio, and we get a little curve over here that kind of shows us as we up that pressure ratio that the thermal efficiency of the cycle does indeed go up. Okay. And notice that the turbine inlet temperature also increases. So after we up this pressure, we're now operating from 2 prime to 3 prime. That could be a significant increase in temperature going into the turbine. I wonder if that could be a problem. Well, it depends on the metallurgy, the metal, the blades, and all that stuff's made out of. It could be. If they're already operating at 3 at the peak and you jerk it to 3 prime, well, we did it in the computer and it looked real good, but when we did it in the real world, it melted the turbine blades. Not so good, So that's always a consideration. Oh, I got the little bouncing ball. And so that's what they're getting to here. So we're going to have another little argument, another little discussion. So if we could already be operating at the temperature limit on the metallurgical temperature limit on the turbine blades, And so let's consider increasing the compressor pressure ratio, but holding the turbine inlet temperature constant. So that's going to look a little bit different because we have to protect the blades. So we'll look at it on TS diagram. Okay, so this is what it looks like. So now we have two different cycles. We've got 1, 2 prime, 3 prime, 4 prime 1, and we have jacked up P2. But we're not going to let the temperature at 3 or 3 prime, they're going to be the same for both cycles. Okay, so it's pretty obvious if I compare these two cycles that this one, this tall skinny one, is going to have a higher thermal efficiency because the average temperature during the heat addition is jacked way up. So the average temperature there is far greater than the average temperature here. That's pretty obvious. And so that's going to favor this cycle. But look at the area enclosed. This tall skinny cycle doesn't have near as much area enclosed as does 1, 2, 3, 4, 1. So that means 1, 2, 3, 4, 1 is producing more work because all of this is per unit mass. So this is going to come out, the area under that curve, enclosed by that curve, is the work per unit mass. So this lower pressure cycle favors work per unit mass, whereas this smaller work per unit mass is created at a higher efficiency. So we get our choice. we can't have our cake and eat it too, as my mama used to tell me. So that's what this is saying. Cycle A has greater compressor pressure ratio, thus greater thermal efficiency. And that has to do with that average temperature during the heat addition. Cycle B has larger enclosed area and thus greater network developed per unit mass flow. So which one do we want? Well, it depends on our application, okay? So the note here is for cycle A to develop the same net power as cycle B, we got to have more mass flow because we don't get as much per unit mass. And that might require a larger system, maybe more weight. And so that might be, if we're doing transportation, I think, is for turbine-powered vehicles where size and weight are constrained, it may be desirable to operate near the compressor pressure ratio for greater network per unit of mass flow and sacrifice your thermal efficiency. So it just depends. Okay. Moving on to discussion of irreversibility. Well, obviously, the biggest irreversibility in all this stuff is combustion, and we're not going to delve. Well, towards the end of this course, we might do a little bit of combustion, but at this point, we're not going to jump into it. Other irreversibilities of interest flow through the turbine and compressor, certainly impact performance. They act to decrease the work developed by the turbine. So as we start looking at real turbines instead of ideal turbines for a given flow rate, inlet condition, and exit pressure, we'll get less work out of the turbine and we'll require more compressor work. So certainly the difference between these is going to be much smaller. So there you go. When you get to real world devices, guess what? You don't get as much as you do when you're dealing with ideal assumptions. Isentropic turbine efficiency. This is pretty much that as we've already been through, so I think everybody's probably pretty good on this. The turbine, it's the real turbine on top because it's going to produce less divided by the isentropic turbine on the bottom. And then just in terms of our enthalpies, 3 in, this is 4 actual out, divided by 3 in minus enthalpy of 4 isentropic out. So that's what it looks like on the diagram. Given your parameters, you just have to go find the enthalpies and plug in the numbers. Or if you don't know 4 and you know this, then you use this equation to solve for 4, which is pretty common. Okay, so I think we pretty well did all that. And then we've got the compressor over here, which functions just like the pump. Numbers are different, working fluids, air instead of water, but the equation works the same way. We put the isentropic on top because this is a work-consuming device. And so we get H2S minus H1 would be the isentropic work. And then the real compressor is going to require H2 minus H1. And we show the entropy increase from 2S to 2. So that's all. I think we're probably good with that. This is just him putting all the labels and tags on it. So that's should be pretty good. Okay, gas turbine power plant loss. So on a simple gas turbine cycle, the exhaust gas is hot. And so, you know, if you really ran a simple system, you'd probably throw that gas away. And you're throwing away a bunch of energy with it. So we've got to address that energy. Okay, so what we can do is we can add regeneration to the cycle. So we can have regenerative gas turbines. And later on, why we're going through all this is to get to the last topic, which is the combined cycle. So we'll get there here pretty quick. Okay, so what we do is we just put in a heat exchanger. Okay, so we got our same compressor. We're just pulling air from outside. We compress it to the high pressure. But then instead of going directly into the combustor, we look around and say, man, we're throwing away a lot of heat over here at 4. Why don't we try to recover that? So we just put that into this heat exchanger we call a regenerator. And so the hot gases from the turbine exit go through and they get cooled down from 4 to Y. And we got pretty warm gas coming out of the compressor. It heats up when you compress it, but not nearly as hot compared to this temperature. So we take that gas out of the compressor at 2 and heat it up some down to X, and then X goes into the combustor. And so that's just going to reduce the amount of fuel that we got to burn in order to make this thing operate. Okay, regenerator. So I think it's just, that's the bullet, you know, process 2X, and the exhaust gas goes from 4 to Y. Get the little balls rolling around in there. And they change, and then change temperature. Preheating reduces the amount of heat added per unit mass. That's the amount of fuel burned. With regeneration, Q dot N is H3 coming out of the combustor minus HX, because that's the inlet state now. Without the regenerator, it's H3 minus H2, which was out of the compressor. So pretty straightforward. The net work per unit mass flowing is the same. However, the thermal efficiency increases because the amount of heat that we got to put in decreases. So that's going to up our overall thermal efficiency in the cycle. Okay, just some discussion about what we can really achieve out there. You know, so this is our hot temperature in, and this is our cold temperature in to the heat exchanger. So what we want to do, we want to get 2 as close to this temperature T4 as possible. The only way we could do that is to have an infinitely large heat exchanger, so we can't do that, okay? So we stop it, we wind up coming out at some point X. Likewise, 4 is reduced to Y. If this was infinitely large, Y would be all the way down here at 2, but again, it's not, because we can't afford that heat exchanger, so it's going to be up. But Y has to be greater than T2, and X has to be less than T4. So we got our little So Tx, as the heat exchanger gets bigger, the temperature difference gets smaller. Tx approaches T4 but cannot exceed it. So it goes up there. And then we get a little stop sign. As the enthalpy of the air varies only with temperature, we also have, that's true of the enthalpy. And so, you know, I saw that statement, that last one, and at first I said, you know, that's not really true. The enthalpy of air also varies with moisture content. But in this situation, let me go back up here, whatever moisture content you have at 4, you're not going to condense anything out in this. So you're going to have the same moisture content from 4 to Y. If the moisture content's the same, then I agree with that. So I'll give him that. Okay, so then we have regenerator effectiveness defined as the ratio of the actual enthalpy increase of air flowing through the cold side, Hx minus H2, to the maximum theoretical. And so the maximum theoretical would be if we got 2 all the way to 4, which we can't do, but we do get from, we get 2 to x. So we take Hx minus H2 divided by H4 minus H2, and that's our effectiveness. And you can multiply it by 100 if you want a percent. So that's regenerator effectiveness. He comments here, typically in around 60 to 80%. It's basically an economic decision. If you buy a bigger one, less fuel, get better performance, but it's a trade-off between fuel savings and regenerator cost. So it's an economic decision. Okay, gas turbines with reheat and regeneration. So what we can do is we don't have to have just one big turbine. We can do a partial expansion, kind of like in the Rankine cycle, and then we can go back, or we don't go back to the boiler, we simply put another combustor in this case. And so we burn some more gas and we boost the temperature before we go into the second stage turbine. One compressor, 2 turbines on the same shaft. Hopefully we get better performance. Okay. So figure shows a cycle with 2 stages, so all that. So basically what we're doing is we go in the first one at 3, we come out at A. If we only had 1, we'd have to drop all the way through, all the way down to 4 prime. And so, but with the reheat combustor, we're going to go from A to B, and then from B down to 4. So you can see what the net work of the cycle is going up. Efficiency is going up because the average temperature during the heat addition is going to go up because we went from 1 to 2, and then we heated from A to B. So when you put all that in the mix, you're going to have a higher temperature. So you're going to get better efficiency. Reheat cycle has larger enclosed area than cycle without reheat, thus greater net work developed per unit mass, which is the aim. And there's the work developed per unit mass with reheat, and it is without reheat. So we pick up that extra little amount that jogs out on the end. Okay, let's see. So what are we doing here? Gas turbines with reheat and regeneration. Oh yeah, we're going to talk about the exit temperature. Temperature at the exit of the second stage, T state 4, is greater than at the exit of a single stage turbine. Accordingly, with reheat, the potential for regeneration is enhanced because I have more temperature exiting the unit. Now, if I didn't recover it, that would be bad because I would be throwing that heat away. So when you do some of these, what this leads to is a more complicated cycle where we put all of these accoutrements in together to make it as efficient as we can. So that's just showing that temperature increase. So if you're going to do reheat, you're really going to want to do regeneration because the reheat makes the regeneration more effective because you have a higher temperature coming out of your final turbine stage. So that's what that's looking at. Okay, another issue that we can get into is compression with intercooling. And let's see, so what we're going to do is we're going to break the compression process down into stages, where we're going to do a partial compression, and then we're going to cool it down, and then we're going to do the final compression. And you can have, it's just an economic decision, you can have more than one stage. It's just you're adding intercoolers and you're adding compressor stages as you go up. Okay, and so what's this look like? Well, if you have just one big compressor, you're going to go in at 1 and you're going to come out at 2 prime. That's it. And the area behind that whole curve is going to be the work. But look what happens if we do a partial, and this is isentropic, that S is equal to C says entropy is constant. We're going to go partially up, and then we're going to cool it down. Well, when we cool it down, we're going to move from C to D. And then when we do the second stage of compression, we're going to go from D to 2. So all this hatched region is work that we don't have to do because we did the intercooling. That's where this is going. So we're going to do it with a little blue ball. So the first stage goes from 1 to C, and then we go through the intercooler. Constant pressure, because it's ideal. We cool down to D, and then we're going to do the second stage of compression, which takes us up to 2. And so isentropic compression without intercooling is just 1 to C to 2, all the way straight up. Okay? So there's our work interpretation per unit mass with intercooling, work interpretation, total work required without intercooling, and that's what you save is the hatched region. So that's a pretty good idea. So man, we're getting all kinds of good ideas relative to this Brayton cycle. So if the total turbine work remains the same, reduction in compressor work results in increase in net work developed, which is the aim of doing it. Okay, so let's look at intercooling with regeneration. I'll put that together. Okay, so let's see what we've got here. So we're going to start at 1. And if we don't do this compression or this intercooling, we're just going to go up to 2 prime. Okay, which would put us here. If we do, we're going to go, up to C, we're going to jog over to D, and then we're going to go up to 2. So notice that the final temperature with intercooling, T2, is lower than T prime. So what reheat, if I remember right, increase the temperature out of the turbine, and intercooling decreases the temperature out of the compressor. Man, this seems like a match made in heaven, doesn't it? To increase the amount of heat, the effectiveness of that regenerator. So it's going to work better. So comparing states 2 and 2 prime, we see that 2 is obviously less than 2 prime. And so that's going to make my regenerator work better. The lower temperature at the compressor exit with intercooling enhances the potential for regeneration. When compression with intercooling is used with regeneration, thermal efficiency can increase significantly over that without intercooling. So TS diagram shows that for cooling to the surrounding temperature, TD at the intercooler exit cannot be less than T1. So this intercooler exit can't be less than T1. Okay, so this is kind of what it all looks like when we put it together. Shown here is regenerative gas turbine that incorporates reheat and intercooling. So wow, a lot of stuff going on here now, okay? So we come in at 1, partial compression, then we're going to cool it off. So we're going to throw this heat away. This is probably pretty low quality. You know, again, a question would be, if you had a particular plant, is there some way to use this? Now, right now, we're showing it here going to atmosphere. Then we compress again. We come out at 4. And so now, because of this intercooling, T4 is lower than it would have been, which makes this heat exchanger more effective. So we come out at 5. Then we're going to go into a combustor, burn some gas, add some heat, come into the first turbine section, come out at 7. We've made some work. Going to add some more heat, burn some more gas, go in at 8, come out at 9, and now we're hotter than we would have been, but it's going to the regenerator, and this is colder, so we're going to make this regenerator work much, much better, and then we discard to the environment at 10. So net cycle work, we got 2 stages of compression and 2 turbines. Okay, so net work output is increased, thermal efficiency is increased. Okay. If now we want to show the entropy increases, then this is what the cycle looks like on the TS diagram. So what 1 was into the first stage of compression. So instead of straight up, you know, you just got an entropy increase you have to deal with. And then this was intercooling, and then we compress again. So instead of straight up, you're at 4. And then the regenerator takes us to 5. Combustor takes us to 6. Turbine to 7. Real turbine. Then another combustor to 8. Another real turbine to 9. And then this is the losing heat in the regenerator to 10. And so I guess that's where we're, basically we end it. We have to, you know, show a heat exchanger or something to close it. So we got to get from there back over to this inlet temperature. And that's what this 10 to 1 would do. Okay. Equation-wise, total turbine work, well, we just have 2 turbines. We got the entire flow through the turbine, so we don't have any extractions or anything to worry about. So that's pretty simple. And if you you can write this with the isentropic efficiencies and just put the isentropic efficiency as a qualifier out front. I mean, I don't know. That might save a couple of lines of math, and you know, instead of going ahead and finding 7, you can just write it in terms of 7s times the turbine isentropic efficiency. Same thing on that. So whichever, basically the same thing. Compressor work in terms of the actual enthalpies or in terms of the isentropic efficiencies. You can write it like that. Let's see. Oh, then this is for the heat added. So we've got 2 combustors, so it's H6 minus 5 and H8 minus 7. And regenerator effectiveness in this case, let's see. Regenerator effectiveness, we're coming in at 4, we're making it to 5, and the potential is what, 4 to I believe. Yep. So it's H5 minus H4 divided by H9 minus H4. Effectiveness of the regenerator. And so we say that, again, we have this limitation that for cooling to the surroundings, temperature of the exit of the intercooler T3 cannot be less than the temperature of the air entering the compressor. So this guy can't be less than T1. Okay. So, you know, basically, we finally get to the combined cycle. So this is another way that this is one way to illustrate. Let me get back far enough. So there you go. We can do all this stuff. And, you know, a lot of this stuff you may want to do in a combined cycle anyway. But another thing that we can do to utilize that waste heat, say one way we can do the regenerative cycle, and the other way is the combined cycle. And this is what a whole lot of the newer power plants are operating on around the country. So here's what we do. Of course, you know, we're just going to show simple components in here, but you can have feed water heaters and all the other accoutrements added in as we will. But so here's our Brayton cycle. You know, compressor, air in, compress it, put it in the combustor, heat it up, put it in the turbine, expand. But we still got lots of hot gases coming out here. So we're going to put in this, it's called a HRSG, a heat recovery steam generator. HRSG is the terminology. And you'll hear people in the industry talk about HRSG. And that's what we're talking about. So basically, this heat recovery steam generator takes the place of the boiler. So we're not, you know, in this simple cycle, we're only burning gas up here in the gas turbine. We put these hot gases into this heat exchanger, basically, and it generates steam for us because we got enough temperature and enough energy going in that we can make high temperature, high pressure steam. And then we're going to run a Rankine cycle on the low end. This would be called the high end because this is where the highest temperatures and all that stuff are. And this would be called the low end. So the HRSG makes steam. It goes into a turbine. We make, you know, we drop the pressure as low as we can. Then we condense, got a pump. And so we just operate our Rankine cycle down here on this side of this thing. So that's the simplest version of a combined cycle. Okay, so I don't think it's going to say much here I hadn't already said, using interconnecting heat recovery. So this, if you work a problem with this, it's a steam generator that basically mathematically chains the Brayton cycle to this, because, you know, you've got your gas flow coming in at T4 and it's leaving at T5. So you got an enthalpy at 4, an enthalpy at 5, and a mass flow rate. And if you assume this is adiabatic, which we would, then all that energy drop is going into your water flow. So you got your mass flow of water coming in at 6 and your mass flow of steam coming out at 7. And there you go. So the amount of energy lost by the Brayton cycle gases as they cool down is the amount of heat picked up by the Rankine cycle that generates steam. Let's see. Combined cycle as gas turbines, higher average temperature of heat addition. That's in terms of our thermodynamic theory. So we have a high value of temperature for the heat addition, and the Rankine cycle's low average temperature heat rejection, because we pull this pressure down so low, this stuff's basically 100 degrees Fahrenheit, give or take a little bit, in the standard Rankine cycle. So it's pretty cold. So that helps. So thermal efficiency is much greater than either cycle would have individually, much greater. Increasingly, combined cycle combined gas turbine vapor power plants are being used worldwide for electric power generation. Yep. So if you remember early in the course when we looked at how the fuel used for electric power generation had kind of shifted from coal to natural gas, these are the cycle. This is what's burning most of that natural gas, are these combined cycles. Okay, so just the equation wise, so it's pretty obvious now that the net power developed is what? We've got two turbines. So we got work out of the gas turbine and we got work out of the Rankine cycle or the vapor cycle. But in this simple situation, we only have one heat input. Now, I'll tell you, in the real Hertzik, they put what they call duct burners in. Duct, D-U-C-T. Lori thought I said duck, D-U-C-K. She thought they were cooking lunch in there. Well, they might do that too. No, they put burners in that hot gas flow in so they can put more heat. So to get maximum steam generation efficiency, they're going to augment the temperature coming out of the gas turbine, because they've done all the calculations and all that stuff, and it's a good investment to be able to burn some more gas to get some more temperature into that Hertzik so you can get some more steam out, so you can get more power out. So all that's been, calculations have been done and optimized. But in this simple thermo presentation here, they don't go into duct burners and all that stuff. That's DUCT burners. For an adiabatic heat recovery steam generator, mass and energy rate balances reduced to give the following mass flow rates for the cycle. So this is where they've done the heat balance around the Hertzik. And so this is the 7 to 8, that's the vapor power cycle. So that's the water flow. M dot V is water. And that's H7 minus H8 is what the water side is picking up. And the mass flow rate of the gases, H4 is coming in hot, H5 is going out cool. So that's just the energy exchange. What's lost by the gas is picked up on the water side. So you just put your control volume around this guy and it just falls out. So it's pretty simple. Okay, now this is pretty slick right here. So this is a combined cycle, but instead of, we're showing a condenser, but we're taking the energy that would be dumped from the condenser and we're taking it into town for district heating. So this puppy would have all kinds of efficiency. Because say we can get, I think the typical combined cycle that TVA runs is 55 to 60% efficient. But that's still running a condenser on the Rankine cycle. If you're set up like this, where you can take that heat out of the condenser and use it for something productive, your efficiency is going to go up another 10 or 15%. So if you were 60, this could be 70, 75% efficient. Or, again, I'm not aware of any industries that run combined cycle plants, but it's not impossible to have an industry situation where they simply have that steam turbine designed to come out at 200 pounds pressure, which is enough then to take out and use for a process. And so then all that heat would be condensed and used in the process, and your energy utilization efficiency would be way, way good, way good. It's just most of them are not designed for that. We're going to do the little ball. Okay, so I think I've said all that. So we're getting electricity, and then we're going to send the condensate return and all that stuff, that heat to town, eliminating the condenser. So that's pretty good. All right, yoo-hoo. We have made good time. Okay, so let's see, you guys are gonna owe me homework. We're not stopping yet, but you guys are gonna owe me homework next time on this Rankine cycle. I've got one more Rankine cycle problem I'll send you. It'll be a combined cycle. I've got a pretty good size one. We got a few heaters here and there, you know, some other stuff, but you got to work your way around one of these things. But let me show you a little bit, just a couple other things here. I don't know. I'm going to ramble now for a little bit. So this is a picture of Magnolia. So each one of these guys is the steam turbine, or the gas turbine is over here, and then it's all integrated together. But there is these are basically, what, 300, somewhere around 300 megawatts per unit. So this is a 900 megawatt plant. And you can see this thing, they're all three operating here. This is the cooling tower for the condensers. So they don't have the hyperbolic. They're running 5 cells per unit, 15. Each one of these motors is 200 horsepower. So they got a megawatt per cooling tower. Let's see, so I don't know. This is flash steam from blowdown. That was one thing we tried to evaluate for them. You still have to do blowdown from the Rankine cycle, keep the steam purity levels right, and that's flash steam. I forget the pressure. It's pretty high, and so that's flash steam. That's pure. Could be used, but it wasn't a tremendous flow. But anyway, this is the air intake back here. We're going to talk a little bit about that some here in a minute. So anyway, I wanted you to see that. Let's see, what else do I want to show you? Okay, well, before I go away from this. So when you operate this gas turbine cycle in the summertime, what you find is that as the temperature goes up outside, the density of the air goes down, right? Higher temperature air is less dense than cold air. Well, the compressors on these units are basically constant volume devices. So if they're operating full out, they can only pull so much volume of air, so many cubic feet per minute, or cubic meters per hour, whatever unit you like. Well, as it gets hotter and hotter outside, each cubic foot or cubic meter has less mass because the density's down. The hotter it is, you bring in a volume of air, you get fewer molecules because it's hot and they all spread out. Well, what happens to your capacity? It goes down because you can't get as many molecules, air molecules, into the compressor, into the turbine, and your power capacity falls. So what can you do? Well, you can do inlet air cooling. And so inlet air cooling on gas turbines is a big deal, okay? And these modules on the back side of this thing, that's where the air comes in, and they have evaporative coolers on these things, okay? And now there's lots of different technologies for doing this. What a great setup. So your next email from me is going to get this pretty good size. So this is a study. Now we're starting to get to some real power industry stuff, okay? We've been dancing around in thermal long enough. So EPRI, Electric Power Research Institute. So that's the R&D arm of the power industry. TVA used to, I don't know what they pay anymore, they used to pay $20 million a year to belong to EPRI. All the big utilities, not only in our country, but around the world, a lot of them join EPRI. EPRI does research. They will let research contracts to various, I mean, Tennessee Tech has done EPRI research in the past. So, but they will fund research that's of interest to a large number of their members, and then they publish the results, and the members get to benefit from that. So instead of everybody running their own research and development program, the industry pools its money, and EPRI runs the research and development. Now, not all of it, but a significant portion. EPRI's home office is Palo Alto, California. We've got a guy, there's a Tennessee Tech alum that's like, I don't know, vice president or something. He had a son, I think, went here a number of years ago. Anyway. So, now you're going to get a thermal assignment, but you're also going to get an assignment to work with this thing. So, well, let's see, where's that little diagram? I had not noticed that lately. Well, this is looking at humid air. This is looking at, they just put that diagram up there. We'll get into that, but let's get down in here to, so this was December of '03. So maybe a few things have changed, but. Here we go. Okay. So look at that. Chapter 2 is inlet air cooling. Evaporative cooling with rigid cooling media. Background, performance of combustion turbines with rigid cooling media. Evaporative cooling with fogging. So background impacts performance. Indirect evaporative cooling. Inlet air chilling, that means like with a water chiller. Buy a big water chiller and make 40-degree water and blow the air across a coil just like air conditioning. That's an idea. Inlet air chilling for base load combined cycles. Man, can you see a good assignment coming out of this? Wow, this is great. Interstage cooling. I think we just talked about interstage cooling, didn't we? Well, this is the real deal of interstage cooling. Impacts interstage cooling on combustion turbines. Stall surge margin envelope, compressor maintenance, hot section emissions, performance of cooling towers or of combustion turbines using interstage cooling. Let's see, page. Supercharging. Wonder what that is. Humid air injection. Wonder what that is. Steam injection. Okay, so we got chapters 2 through 6 here. And so when you get this thing in the mail, you're going to have a week. And I want you to take each one of these sections and I want you to look over it. And I want you to write me a paragraph or two in your own little words. Just say, what is this? Tell me what it is. Some kind of an idea. Is it effective? What do you think? Because see, these are different, a lot of these things are competing technologies for the same goal. You might give me a statement in there at the end of some of these, they might not all apply as well. But up here at 2, like, wow. If you were going to do something, say you're an engineer for TVA, and you've been asked to give them recommendations on a new combined cycle plant. Which one of these technologies should they use? What would you recommend after you've looked over this? Would you recommend foggers? Would you recommend rigid media cooling? Okay. So, I mean, I'll be flexible on due dates, but this is really good. I mean, this is a pretty good document. I mean, and it's at the industry level. I mean, some of the technologies may have changed a little bit in 17 years, but we got into some of this stuff at Magnolia, and I mean, that's where I dug this up. I've got umpteen of these EPRI reports on combined cycle plants, but I thought this one was pretty good. And after coming out of this Brayton cycle discussion, I thought it'll, I think if you'll dig in and read a little bit, and you don't have to do it all in one day, I mean, pick a chapter, and some of these are longer. Some of them are pretty short too. So, read 4 or 5 pages, jot down your thoughts, and take some notes, and then you can write it up later, whatever. I mean, I think it'll be a good learning exercise for you if you'll follow through and be pretty conscientious with it. So you'll be getting that from me shortly. Okay, let's see. Do one other thing here. Okay. So this came out of our study. There's some pictures and some things from Magnolia. I'll send you this too, just for your library. I don't think TBA care. Okay, so we were inside the casing on these combustion turbines, and we had infrared imaging camera. And we're just looking around. I mean, I'd never been on the bowels of a combustion turbine before, especially when it was operating, which, I mean, it's just, you just go in a door, and I mean, you got your ear protection on. It's a little bit loud, but I mean, it's safe. And what we discovered is what they have. So these compressors they have multiple stages of compression. So they do a lot of intercooling. And I forget, it seemed like they said it was the 3rd or 4th stage of compression, where they had pretty good temperature in the compressed air. They had some, I don't know, you'll see pictures of them, 4, maybe 6-inch pipes that came back. And the idea was that air, that hot compressed air, it was pretty warm, could be sprayed out at the inlet, because if it gets too cold outside, you'll get ice crystals will form, because as that air gets sucked up into the compressor, the pressure goes down and down and down, and that's a cooling effect. And so you have to be careful about pulling ice crystals into this. And so these ducts were to take this part of the hot gases and take it down and spray it out at the inlet when it was too cold outside, in order to not have ice crystals form. So this was a loss. I mean, when they did that, it was a loss of capacity. But it was also when it was cold outside, and so the air had a lot of density, so they had kind of competing effects there. Well, we're there in the summertime, and we're in there shooting around on all these pipes and these valves, and all of a sudden, man, that valve, and you'll see a temperature, that valve's 300 degrees sitting up there. I said, hey, Pete, whatever the guy's name is, I forgot now. What is that? What are all these pipes? You just in there, and there's crap running all over the place. He looks in there, he says, oh, that's those are the reheat lines for the wintertime, so we can heat up the air when it goes into the compressor, so we don't make ice. And I said, well, it's 87 degrees out there. Do we need to be heating up the air today? And he says, nah, it's those doggone valves. The valves that I think GE sold us on those things, they keep failing. And so that valve's leaking through. Well, so how much of a loss is that in terms of generating capacity when because they got 3 units operating. So we went around, and so this is a picture of some of the lines. That's like expansion stuff. So what that's a 6-inch line, I believe. So there's 2 of them there. I think we had 4 of them per unit right there that we could look at. Yeah, let's see. So that's, yeah, okay. So the door, you can barely see the opening of the door. So these 2 lines ran above the door, and then these were on the back wall. So there's 2 more, and there's 2 of the valves that you see. They're like automatic valves. Okay. And that's, okay, so this is, yeah, this is CT1. It's been a little while since I looked at this. That's CT1, valves by the door, CT1, valves on the back wall, C2, CT2, you know, likewise. 3, there you go. So we got 6 of these. Oh, I'm sorry. It wasn't 300 degrees. It was 513 degrees. And you're sitting there, you know, sitting around looking at that. And this is a picture of this area. So this is what the infrared camera showed. Sitting there going, whoa, 513 degrees, what are we doing here? He said, I had valves leaking through. So then the question is, you know, it doesn't look like it's completely wide open, or I think that pipe would be hot further. You know, looks like it's kind of coming, or maybe it's coming down from here. I'm not sure what the flow pattern was, but anyway, so we had this guy. Let's see, that's CT2 hotspot. There's C1 leaking, valve by door, bottom pipe. And so you can see right here, it's at the spot, now that's based on emissivity, right? And you have to kind of guess the emissivity. So, but I mean, it may be 5 or 10 degrees wrong, but if it shows 342 degrees, you don't want to put your hand on it. I promise you that. So it's pretty hot. So over in here, it's seeing the white is 376. So it's pretty warm. That's the bottom pipe. That's the top pipe. So CT1, there's 2 of them. Now see, there's one that's good. So that's the back wall bottom pipe. So the 2 on the back wall look pretty good because it was warm in there, and you know. Okay. So bottom pipe, CT2, 325. Doesn't look as intense as this one though. $371, CT2. So it seems like the one on the back wall, we're not leaking as bad. I don't know if it's a different valve or what. There's bottom pipe, CT3, and there's a little bit. So there's a back wall, a little bit of a leak in that. So anyway, we presented all this to TVA and talked to them, and then, so the question was, I mean, you see something like that, how do you evaluate the potential cost? That becomes a pretty good trick. So we had a meeting in Chattanooga and talked to, I forget the guys, there's several people down there that were in their gas turbine groups, and they were supposed to take this and try to do a little evaluation or give us some guidance on how to predict potential savings. And I don't think they ever got back with us. I also reached out to GE, whose valves it was, to see if they had some gas turbine people that wanted to talk to us, and they didn't get back with us. We didn't get a lot of respect in some regards on that. But at any rate, I thought that was related to this topic. Okay, I think that's probably enough for today. I'd be looking for emails from me, and I'll be sending you out some more information And we're going to start, I may dig up a little more on combined cycle, but we're going to start into the Babcock and Wilcox boiler information next. So that'll be a pretty good size block. Once we finish all this thermo stuff, get all the homework assignments in and looked at, then we'll be looking at our first test. So probably not next week, probably week after, we're probably looking at a test in here. So anyway, okay, hope everybody has a great day, and we'll be back in touch soon. Take care.
I have a quick question.
Yes, sir.
How will the test format be? Will it be like the homeworks where we're solving like a cycle or something like that? Or will it be like the quiz where it's a multiple choice test?
I haven't made it up, you know, everything's got to be kind of reformulated for this iLearn environment. I expect there will be a lot of the test will be small individual problems. You know, for example, I might pick the concept of an isentropic turbine efficiency. So I may give you a scenario where you just calculate an enthalpy. I might ask you to, I might give you a big cycle, but then ask you, well, what's the backwork ratio? What's the boiler rate heat input? This, that, and the other. Yeah, you try to make it so that it doesn't change. Like if you make one mistake on one enthalpy, that causes you to miss 3 different questions, you know, because that's one mistake and you're getting penalized 3 times. So that's kind of painful, you know. So the idea is I want you to do calculations primarily, but now so we've got power factor and rate structures too. So that's going to be on there. So you'll probably have some sort of, you know, power factor is a nice little problem. You know, I can give you 3 or 4 numbers and, you know, draw a power triangle and show it to you and ask you to calculate something out of that. I could give you some billing information and say, okay, calculate the demand charge on this bill. Calculate the energy charge. Calculate the off-peak energy charge. Calculate the on-peak energy charge, something like that. So those actually break down pretty well to short. So I want it to be a bunch of short calculations. You know, now how much is a bunch? Probably not 30. That'd probably be a little aggressive, but probably more than 10. And then there might be some true false multiple choice, you know. I'll give you more feedback on that, but it'll be on iLearn, and a major part of it will be, you know, fairly short individual problems that you have to calculate and then match an answer. That help?
It does. Thank you.
Okay. Anybody else? Okay, guys. Thanks a bunch. See ya.